Hello, this video is for Stat 210, handout number 12. Okay, let's go ahead and get started with handout 12. So handout 12 includes an understanding and investigation of the relationship between two numerical variables. So we're going to do what's called simple linear regression here, is the topic that is being covered. The first example that we're going to look at is an example that we looked at in handout number 12, and it is the agreement between Dr. A and Dr. B. When we looked at this earlier in handout 10, I believe it was, we learned that Dr. A, on average, found about 2 to 4 more palpal lymph nodes than Dr. B did. Here we're going to look at the relationship now with an investigation of scatter plots between the two variables. So when I'm interested in doing scatter plots, what I'm going to do is just put the two variables that I'm interested in. One's going to be in the response, and the other is going to be here in the X factor box. So here I've placed Dr. A on the X-axis and Dr. B on the Y-axis. Inside a jump, I can use a fit special, and by constraining the y-intercept to 0 and the slope to 1, what I'm actually going to do with that is place a y equal x line on that plot. And that's important because that's where I have agreement between Dr. A and Dr. B. So why don't I go ahead and show you that quickly and how to do that inside of jump. So here is the data. Here's Dr. A, Dr. B. So we're going to go analyze, fit y by x, Dr. B in the response box, and Dr. A here in the X factor box. I get my scatter plot, which will bring that into view here. And now underneath my fit special, here I can constrain the y-intercept to 0 and the slope to 1. And then that will put the y equal x line in that plot. Now it doesn't look like it's the y equal x line. It doesn't go exactly from corner to corner. That's because the two scales are different. So let's match up those scales quick. Just go from 0 to 20. And then let's force, that one's already from 0 to 20. So that there is the display that we have in the notes. Now, looking at the display here in the notes, we can see that most of the dots are below this y equal x line. So what does that mean? If we pick on a point here, let's pick on this one right here. It looks like Dr. A found maybe 12 there, and Dr. B found about 6 there. So any of the dots on the lower side of this line means that Dr. A was finding more. Any of the dots on the high side mean Dr. B was finding more. The ones that fall exactly on the line are going to be complete agreement here. So it looks like out of the 30 or so scans that they looked at, 3 times they matched exactly. 4 times Dr. B found more, and then the rest of the time Dr. A found more. We can add a trend line in there. So if I just, from my drop down, select fit mean here, I can get my trend line in there. And we notice that the slope is flattened a little bit. So the slope of my y equal x line is going to be 1. But this here is a little bit below 1. It's a little bit flatter than the y equal x line. And what that means is that for each additional, for a 1 unit increase in Dr. A, Dr. B is not increasing by 1, but something slightly less than 1. Okay, so the fact that what this means out here for the high numbers, Dr. A is finding quite a bit more than Dr. B is, right? The gap here is quite large here when the number of palpal lymph nodes is large. We'll talk more about getting this trend line and some interpretations off of that trend line here later. Here, what we're looking at is the capstone project that was done by Dr. Jen Anderson and her student, investigating the impact craters. So if I grab that data quickly, bring that into view here. To get the graphs that I used here, what I did is used Graph Builder. So select graph, graph builder. I place the height on the x-axis. So that's the height that the projectiles were being dropped from. And then I have diameter here on the y-axis. Now the default plot that is created is just for all of the different combinations. So the different projectiles here and also the different sand types are in here. But you can certainly see that as the height increases, the diameter increases. A spline is being fit here instead of a straight line. So if I wanted a straight line, I could select that. That's going to be a regression line there. But I'm going to just leave it as what we call a spline fit. Sometimes they're called a low-S fit. Now if I want to break this out by the projectile type, what I can do is drag projectile type over to my overlay. And then I can get some differences between the wood ball, glass ball, and the steel ball here. So let's move this out of the way, and that's the graph that I created here for us. Oh, get that out of the way. That's the graph that I created here. So certainly you can see that the wood ball, which is the green, is lower on the diameter compared to the steel ball. And this is just a function of the weight of the ball here. So the wood ball is quite light, the steel ball is quite heavy. So if the object is heavier, you're going to end up with a larger diameter being created in the impact crater. They do look fairly parallel to one another, except here for the steel ball. You can see that that gap isn't quite as much as in their other parts. So that means when the steel ball is dropped from a very low distance, it's acting more like the glass ball there, right? They're getting closer than, say, on this end. We can also look at the WSU vitamin data, which we looked at that previously in Handout 10 and also a little bit in Handout 11. But here, the reason I'm looking at it again in Handout 12 is because I wanted to look at the effect of BMI. So BMI is on the x-axis here, which is just body mass index. I have energy difference, okay? So this is the difference between actual and DRI. And then the two colors here are for males and females. And you can see that for females, this red trend here, again, these are just spline fits or low-S smoothers. The red tends to stay under the line of agreement there, or the target. So that horizontal line at 0 means they're on target. And the red here is females, and they tend to stay under that. Now, the line is fairly flat, which means that BMI really is not influencing, okay, the amount that a female is undereating or overeating. On the other hand, the line for males is not flat, so BMI does have an impact on that. It looks like basically from 18 BMI up to about 22 or 23, males are doing pretty good. And then when you get up into these higher values for BMI, it looks like the males tend to start to undereat more, at least on average. So this blue line tends to drop off quite a bit when we go from about 23 up to 26 on the BMI. It's more consistent with females. The degree of undereating as a function of BMI is more consistent for females than it is for males. If we look at the vitamin A, it's pretty even there. If anything, women are closer to target than vitamin A than men are. Vitamin C looks pretty good. We do have quite a gap here in calcium. So the males tend to do, if anything, a little bit above their expected calcium intake. So males are doing good here, whereas females are under what they should be. Again, that line is fairly flat. It's a little bit better for higher BMI. They're closer to their target here of 0 for the higher BMI. And this is iron here. Males are significantly above their iron. So they're taking in more than their DRI says for iron, whereas women are pretty close to the target there. So again, in these plots here, we're looking at difference between actual and DRI. We're looking at effect for gender, and then we're also looking at an effect for BMI. So we're considering 3 different variables there simultaneously when we're looking at these plots. Okay, let's look at our last example, which is a little bit bigger here. And this is a study that was done at the Winona Clinic. And we're going to look at bone density between the forearm, and then the more accepted ways of measuring bone density are to measure bone density either in the spine or the hip or the neck. So what we're trying to do is measure bone density in the forearm, which is actually an easier thing to do. It's less costly to measure bone density in the forearm. The more expensive measures is the spine, hip, or neck. That requires a bigger machine that costs more. That costs more to actually do those scans and such. So the individual that I was helping with a study was trying to figure out whether or not forearm could be used as a substitute for spine. The measurements for bone density are just T-scores, which are actually just standardized values. So normal would be somebody that has a T-score of -1 or higher. T-scores less than -2 would mean that you are diagnosed with osteoporosis. And then between -1 and -2.5, we have precursor to osteoporosis, and that's osteopenia. Okay, so let's go ahead and look at a scatter plot between forearm and spine here. Okay, and again, we're going to set up a display like this here. So maybe I'll show you that quickly. So let's grab the T-score data. I'm going to look at the relationship between forearm here and spine. Okay. Bring that plot into view here. Again, this is I would like them to match. So we are going to go and try to align these scales. So let me just do that. I'm going to go from -3 to 3. And then I'm going to go from -3 to 3 on this scale. Can put grid lines in there if we wanted. I want to add or snap a y=x line again because that's where I have agreement. So I did that under fit special, I believe it was. 0, 1. So that's my agreement line. I can change the color on that if I wanted, and style. If we can make that dotted maybe. Maybe make it a gray to kind of set it in the background a little bit. Now -2.5 would be here and down in this corner, right? So that would be where they have osteoporosis on both the spine and the forearm. So I don't have anybody down here in that corner. But I do have -1 as osteopenia. So maybe let me make a reference line at -1 for us. And maybe make that red or something to have that stand out a little bit. And then make another one over here, -1, make that red to have it stand out a little bit. So these two right down in here are going to have osteopenia on the spine reading, and they're going to have osteopenia on the forearm reading. So I have agreement here. Both the forearm and the spine is indicating osteopenia. I have 1, 2, 3, 4, 5 here where the spine would be indicating osteopenia, but the forearm is not. So these are bad here. All right? Bad in the sense that my two testing methods for bone density do not agree with each other. And we want the forearm to be able to detect problems with bone density. Spine is kind of the more accepted way of measuring bone density, and for these 5 patients here, out of the 40 or so that I have, they do appear to have problems when I'm using the spine because it's less than -1, but the forearm's not picking that up. And then the opposite is true over here. The forearm picked this one up where the spine did not. But these 5 over here are problematic if I'm trying to look at the amount of agreement between the two. If I throw my trend line in there, that's just under fit line. And you can see here with the green, this is definitely higher. This end is the problem end. This end is when bone density is degraded here. And you can see that my forearm is definitely over-predicting, okay, the spine scores here. If they were matching, it would be close to the y=x line. So if we wanted to actually fit the model and get all the output for this green line, let me show you how that's done. We go underneath Analyze, Fit Model. Okay, this is a new framework we've used here. AP Spine is going to go down in my Model Effects, and then my forearm is going to go up in the response here. And then hit run, and I get a collection of output here. We're going to look at this top plot as just my scatter plot. Again, the scales aren't exactly the same here, but this is the plot that we were just looking at. The red line here is exactly the same as the green line in the other plot. And then I got a bunch of output down here that we are going to look at. Kind of the main part of the output here is underneath the summary of fit. And I've included that in our notes, and we'll talk about some of the values in that summary of fit now. We'll start with test number 1 and 2. Okay, actually number 2 is much more important than number 1. This is the y-intercept of my line. And this is the slope of my line here. Okay, so these are actually testing whether or not the true y-intercept is 0 or different than 0. So that's going to be test number 1 here. Okay, so the p-value there is 0.0058. We want to put that in there, 0.0058. The decision is that this is less than 0.05. So data supports the HA here. Okay, and that's going to say that the y-intercept of my true regression line, again, these vary, right? This is the regression line I got from my situation, but you can think of that as varying repeatedly over and over and over again. So do I actually have a difference at the y-intercept between my regression line, which is the red, and what it would look like if it went through the origin? So this is saying here that the true y-intercept is different than 0. So I do not have agreement here at the origin. So this red line is significantly off of what it would be if it went through the origin. Now that's just testing at one spot. If we test the slope, okay, so that would be p-value number 2 here, 0.0001. So that's less than 0.05. So that's going to say that my slope is definitely not equal to 0, which makes sense. This is a useful test because this is testing whether or not I actually have a relationship between spine and forearm. Right? If the slope was 0 or flat, then it would say that I don't have a relationship between spine and forearm. But by the fact that this p-value is less than 0.0001, I can say that I definitely have a relationship between my spine scores and my forearm scores. So that makes sense. There is a relationship between these two. Again, that doesn't necessarily mean that I can use forearm as a substitute for spine, though. To test the y-intercept equals 0 and the slope equal 1, okay, so that's a typo there, and the slope equal 1, so this is going to test the relationship between my regression line, which is the red line, and the line of agreement. Okay, that's different than what we did up here. I was testing these individually. This was agreement at the origin, and this was just determining whether or not I had a relationship between spine and forearm. Okay, that's different than this test here. This test here is testing whether or not I have, can I say that I'm close enough to the line of agreement? To do that, it's a custom test. I'm not going to be too worried about. I'm not going to make you guys do this, but this is saying that I do not have agreement here. My p-value is less than 0.05. That means the HA is true. So something's off there. I do not have agreement between my regression line and the y equal x line. So that is telling me that I cannot use the forearm as a substitute for spine, which you probably gathered that because when we were looking at that initially, it was quite, where was it at? It was quite far off here, especially down there where it really mattered. Do some real quick summaries of this, and then we will be done with the video here. If you want to make predictions, okay, to make predictions, I'm going to get these values right here, these estimates. So that is the estimated y-intercept and the estimated slope. So about 0.3 and then 0.6. So that's going to be my equation of my line there. And if I want to make a prediction for a forearm score, I would just enter in somebody's spine score and I could get a prediction out. There's going to be certainly errors in those predictions. So not all the points fall on my regression line here. So that's what the RMSE number is about. So let's go grab the RMSE number up here. The RMSE number, the root mean square error, is 0.641. So 0.641 is going to be the average, 0.641 here. And that is going to be the, that is going to be the average amount of error in my prediction. So if you look at the graph here in the next page, that is the average residual value or error value. If the average residual value is really small, that means my predictions are going to be more accurate. Here, if my average distance back to my regression line is quite large, that means my predictions are less accurate. So here, this looks fairly large. Obviously, some of the points I do pretty good, but in others, I'm quite a ways off. So my standard deviation here in my predictions, or my RMSE, is fairly large, especially considering what these forearm scores look like. Right, they're from -1 to 1, and my error here is 0.641. So I am quite a ways off on my predictions. Real quickly, the last summary that I want to talk about is the R-squared value. The R-squared value has to do with the reduction in the variability when I look at the relationship between spine and forearm. So what was the variability in just forearm by itself without taking in consideration the spine? That is just going to be the standard deviation in the forearm measurements, which turns out to be 0.88 here. Okay, and then I'm going to compare that against what was my error. Okay, when I did error in forearm scores, when I did take spine into consideration, and that's just my RMSE value here. So R-squared is looking at this number here relative to this number here. Okay, or a function of this number here and a function of this number here. Okay, now when we do the R-squared, we actually are just using the numerator here, 1559, and the 30.50 here. So we're going to compare those two. That is the R-squared here, 1559 divided by the 30. So that's about 50%. So what that means is 50% of the variability in forearm can be explained using a spine score. So let me type that in there. So about 50% of the variability in forearm score can be explained by the spine score, T-score, right? These are all T-scores. Get that typo. So about half the variability in forearm, so I'm talking about the variability in the forearm, can be explained using the spine T-score. Now, if this number is high, it's halfway there. It's between, this number is between 0 and 1, or 0 and 100%. If 100% of the variability in forearm can be explained by spine, that means that spine is going to be a perfect predictor for a forearm score. Now, I don't have perfect predictions. I have errors here, right? Where's my residual plot? I have errors here. So I don't have perfect predictions, but I'm about halfway there. I can greatly reduce the variability in forearm scores by taking into consideration spine scores. So we want that R-squared to be as large as possible. And if it is up to 100%, that means the predictions will be perfect. You will have no errors in your predictions. There's a little bit about the assumptions, but I'm not going to worry about that this semester. So we will skip the last 2 pages there of that. So there we go. That is the handout number 12 video. Thank you very much and have a good Thanksgiving. Bye-bye.